This is the second part of the presentation about part-of-speech tagging. In the second part, I'm going to talk about how we can use hidden Markov model for part-of-speech tagging. If the name Markov rings a bell on your mind, or it sounds familiar to you, well, you're quite right if you think about Markov chain. Markov chain can be said as a model that tells us the probabilities of sequences of random variables, or you can call it states. For example, there are 3 states of weather. The weather can be hot, the weather can be cold, the weather can be warm. Now, Markov chain will tell us what is the probability that we are in a particular state, and then the next period we are going to be in the other state. Or there's also a probability that we stay in the same state. The idea is that what is the probability that we are at a particular state at a particular time or period. One of the most important assumptions in a Markov chain is this. So when you ask what is the probability that at time I you will be at state A. Okay, so for example, you're asking what is the probability at time I the weather will be hot. And then the history that you're going through so far is you have the history from the weather from day 1 to day I minus 1. Now the assumption of Markov chain or Markov model saying that the probability that today's weather is A only depends on the previous day or yesterday. So you don't need to care about the history from day 1, day 2, day 3 up to day minus 1, but you only need to care about the previous day. So when you ask what is the probability that today's weather is hot, Markov model says that you only need to care about yesterday's weather. Now let's try to bring the context into the part-of-speech tagging problem. In the case of part-of-speech tagging, we can observe the sequence of words. We can see the sentence, we can see the order of the words, so we can observe that. But the sequence of the part-of-speech tags is hidden because you can see the word, but you don't know what are the part-of-speech tags for each word. It is a bit different with the case of the weather in the previous slide. For the weather, every day you can observe the weather directly. Like you know today is hot, you know that yesterday was cold, 2 days ago was hot, and so on. Everything is observable. That's why it's called this Markov chain. And the problem of part-of-speech tagging is called hidden Markov model, because the thing that we are interested at, the part-of-speech tag for each word, is hidden. We cannot observe them. We do not know that whether this word is a verb, is a noun, or whatever it is. We can only see the observations, the words, but we cannot see the tags. The tags are hidden. So an HMM or hidden Markov model allows us to talk about both the observed events and the hidden events. Again, the observed events are the words that we see in the input, like the given sentence to us, we can see every single word in that sentence, but the hidden events are the part-of-speech tag for each word. Okay, so the contrast between hidden Markov model and the usual Markov chain model is that in Markov chain, all states are observable. We can observe them all. In hidden Markov model, there is something that we are interested at, but it is hidden. Now, this is an illustration of a hidden Markov model. So what we can observe or what we can see is that, for example, we are given this sentence: the aardvark, the zebra. And then these are the possible tags. For example, there are only 3 possible tags: verb, model, or noun. And then, so the hidden Markov model will show the probability of transitioning between this tag, which we cannot see, and what we can see, in other words, what we observe in the sentence, is when the tag produce a word. So noun can produce all this word with certain probability, and after the tag produce the word, then we can see the word. So we only see this part, what is produced by the tag, but we cannot see the tag itself, and then we cannot see the probability of transition between one tag to another tag. So that's the difference with the Markov model. In the usual Markov chain model, all these states are directly observable. You can see, you can observe the weather. Here you cannot see the tag directly, but you can only see what is produced by the tag. So this is an illustration of part-of-speech tagging modeled as a hidden Markov model. Let's talk a little bit more about the components in a hidden Markov model. So these states are called states as in the Markov chain model, although you can say they're hidden states. These states are called the states. The thing that we're interested at, but we cannot see or observe them directly. And then the probability of transition between one tag to the other tag is called transition probability. And then when the tag produces words with certain amount of probability, we call this as emission probabilities. So the tag produces words based on certain probabilities, and then we call those probabilities as emission probabilities. The probability that this tag produce or emit that word. And then the words that we see in the sequence of the words or in the sentence are called observations, because we can observe them, we can see them directly. Okay, so these are the components of a hidden Markov model. Now I'd like to emphasize another important difference with the ordinary Markov chain is that we have 2 sets of probabilities in hidden Markov models. In a usual Markov chain, you only have the transition probabilities from one state to the other, but in hidden Markov models, we have the transition probabilities and we have the emission probabilities. So 2 sets of probabilities instead of just one transition probabilities as in the usual Markov chain model. Now let's define the part-of-speech tagging task in an HMM setting. So we're given a sequence of observations. So here, let's say we have word 1 up to word n. So if you recall, the symbol means a sequence of words from word 1 up to word n. Here the n is 5, and then the first word is Janet, and the second word is Will, third word is back, fourth word is the, and the fifth or the last word is Bill. So that's the sequence of observations that we are given. So we can see it, we can observe it. Now our task is to find the most probable sequence of states. In other words, out of all possible sequences of 5 tags, we choose the sequence that is the most probable for that sentence. So in other words, we have to determine what is T1, T2, T3 up to T5, whether, let's say, T1 is a noun or verb or adjective, The same with T2 up to T5. So we need to find the most probable sequence of states out of all possible sequences of 5 tags. So we can say that thing in an equation like this. So here it means that out of possible sequences of tags, we would like to find the one that maximizes the probability that given these are the word sequence that we see, this is the sequence of tag. So we want to find which sequence of tags gives the highest probability given that the observation that we can see is this sentence here. So here TIN with a hat means that the answer or our answer is that among all possible sequences, we find the one that maximizes this probability, the probability of that sequence given the observations that we see. Now, how to calculate this probability is a bit unclear. Like we are given a sequence of words and then we have to compare among all sequences of 5 tags and pick the maximum. The idea is okay, but then the practice is difficult. How can we calculate this equation? Now let's see what we can do to simplify this equation. So first we may apply the Bayes rule. So the Bayes rule is our probability of P given W, and then you expand this using the Bayes rule to become like that. And then we may drop the denominator. Why? Well, because the probability of the words will not change regardless of what tags you're giving to each word. The probability of that word to occur is still the same. I mean that whether your tag is right or wrong, the sentence is still the same sentence. So it does not depend on our task here finding the tag. The probability of the word does not depend on the probability of tags. Whatever tag you are given to each word, the probability of the sequence of that word is still the same. Janet will pack the bill, the probability of that word is still like that, regardless of your saying that Janet is a noun or a verb or an adjective. For that reason, we drop the denominator. Now we'll look at these two terms in this equation. For the first term, we want to find what is the probability that we see that word sequence given the sequence of the tags. And then the second part of this equation is probability that we see the sequence of the tag from 1 to n. Let's see the first term. We put an assumption saying that a word at a particular position only depends on its tag. So it is independent of the neighboring words, it is independent of the neighboring tags. The previous tags doesn't matter, the previous words doesn't matter, the next tags, the next word does not matter. The probability that we see a word at position I depends only the tag at position I. And then to get the probability of word 1 up to word n, we just multiply this probability from the position 1 up to position n. So now we calculate this term with the probability of seeing word 1 given that the tag is tag 1 times probability of word 2 given the tag is tag 2 only. Probability of word 3 given that the tag is tag 3 only. So we simplify the matter from sequences only from sequences to only the tag and the word at the position I. And then for the second term of the equation, we put an assumption saying that the tag at a particular position depends only on the previous tag. So when we want to compute the probability of seeing the tag from tag 1 up to tag n as a sequence, we break this down with each position. So the probability of tag I only depend on the tag at position I minus 1. Okay, so when you want to calculate the probability of the tag, you're seeing the tag at tag 3, for example, you only need to look at tag 2. So that simplifies the matter from sequence to just seeing each position and the one position just before that. So now we combine what we have done for the first and the second term. So now this is the final equation that we have. And then if we look at this terms here, the second term is the transition probability. The probability that the tag changes from one tag to the other tag. So this is the transition probability. Probability of moving or changing from one state, even though it is hidden, from one state changing to the other tag or state. And the first term here is the emission probability. Remember, emission probability is that given a tag, what is the probability it will produce a particular word? So this equation has captured the two probabilities that we have in the HMM. First is the transition probabilities, how the state changes from one state to another state. And then it also captures the emission probabilities. Given that the tag is tag TI, what is the probability that this TI tag will produce the word I? And then we multiply these probabilities from position 1 up to position n. So now that we have seen in the previous equation that we have both transition and emission probabilities, how exactly can we compute those probabilities in practice? Well, first, if you have a document that is already tagged correctly, so you have a document and then every word in that document has been tagged, you may count the transition probability by counting. So you count how many times the tag TI-1 appear, and then you count how many times the tag TI-1 is followed by the tag TI. So that becomes the probability of saying that, okay, after the tag TI-1, the probability it will be followed by the tag TI is this value here. So for example, in the Wall Street Journal corpus, the probability that the previous word is a model, the probability that the model will be followed by a verb is that first you calculate how many times the model tag appears, and then you also count how many times the model how many times the model is followed by the verb. Apparently, the probability of this verb following a model is pretty high. It's 0.8. So model is something like can, could, may, might, and so on. VB is the verb in a basic form. like eat, jump, learn, use without s, without ing in the end, so just the verb at the base form. Now it's very similar with the emission probability. Like you want to know what is probability given the tag is tag ti, what is probability it will produce the word wi. So what you're doing here is that you count how many times the tag ti appears, and then you count how many times the word ti produce the word wi. For example, you want to know how many times if the tag is MD or model, how many times that the word it emits or it produces is the word will. So you count how many times you see the word, how many times you see the tag MD or models, and then you see how many times that the tag is model and the word is will. So apparently, out of all models that we see in the Wall Street Journal corpus, about 31% of them is the word will. So will is, so if you see the tag is model, then there's a probability of 31% that the produced word is will. So this is an illustration of what we are going to do in finding the correct text. So suppose the sentence is as before, Janet will back the bill, and these are the possible tags that we have. So let's say we have 3, 4, 5, we have 8 possible tags. So what we need to do is we need to find the sequences that gives the highest probability for the tags given that we see the sentence is Janet will back the bill. So we need to consider all the 8 possible tags for each of the word, and then we try to find the best sequence. So this is what we're going to do with an HMM. Let's walk through an example to see how an HMM works. So we are given a transition probability matrix. We'll see this on the next slide. We are given the emission probability matrix, also on the next slide. And we are given the sequence of words. Janet will back the bill. We will use something called as a Viterbi algorithm, such that we may find the correct tag for each word. So for example, Janet is a proper noun, so we should find the correct tag for Janet, which is proper noun. Will is a model, back is a verb at a base form, the is a determiner, and then bill is a common noun. So we try to find these tags. These are the matrices that I talked about in the previous slide. So the transition probability matrix usually is called as matrix A. It shows the probability of transitioning or changing from one tag to the other tag. And then if you see the symbol, it means the start of the sentence. So let's take an example. So let's say this point 0002. It means that if the previous tag is model, the tag at this position is also model, has the probability of 0.002. However, if the previous tag is model, then we have a very high probability, 0.7968, that the current word that we're seeing has the tag of verb in the base form. Okay, so this table assumes that we have only 7 3, 4, 5, 6, 7, and 8 with this start symbol, we have only 8 possible tags. Now, in the bottom part of the slide is the emission probability. Sometimes it is called the matrix B. So in the matrix B, you can see that if the tag is noun and it's a proper noun, then probability that it will produce the word Janet is 0.000022. Of course, it is very small because you have so many proper nouns, and then Janet is only one of them. Remember, proper nouns can be something like England, Congress, Rachel, Richard, Janet, and whatever. Let's see another example. If it is a common noun, then the probability that the word is Janet is 0. Okay, it makes sense because common noun is not something with a specific name like Janet. Common noun is like door, a goat, clock, time, computer, and so on. So the probability that if the tag is noun, the probability it will produce the word Janet is exactly 0. And this is exactly 0 because the example here is done without smoothing. Remember that if we have smoothing, then all these 0 probabilities will be given some values to avoid the zeros. But at this moment, let's just be it. We have probabilities without smoothing. So we have 2 tables here. The first table is the transition probabilities, and the second table is the emission probabilities. Transition probabilities show the probability of moving from one tag to the other tag. Emission probability shows that if we have particular tag, what is probability that it will produce a particular word. So this is an illustration of a Viterbi algorithm. So let's see here what are these components. So on the bottom you see that these are the words that we can observe. It is given. Janet will back the bill. And then in this part here, you see all the possible tags that we consider. So we have 7 possible tags that we consider. And then what we have here in each of the boxes here, let's say we have V27 up there. So it means that the probability that the HMM is in state 7. So state 7 is the tag determiner. After seeing the first T observations, so T is 2, and passing through the most probable state sequence. So the value in this box here, V27, should tell us the probability that after seeing 2 observations, or we can also say in the second word, we see that the state is state 7 determiner with this probability after we pass through the most possible sequence. So let me say it in another word. So in another word is that the best probability, the best sequence probability that lead us to this position. So what is the best sequence probability that we have had such that now we are in the second word, state 7. So we only record the best sequence probability that has led us to a particular position. It may look a bit complicated, but actually it's quite simple. We'll see this in the next slides or so about how to compute these values here. Okay, now let's start from the sentence that we are given. So our sentence starts with the word Janet. Remember that we put the start symbol at the beginning of a sentence just to make us know that, okay, that is the first word. Janet is the first word. So the word at the position 0 is the start symbol. Now let's see what is the value at this box here, V17. So V17 is that the probability that the first tag is the start symbol, and then it will be followed by the 7th tag determiner. Why the 7th tag? Because we are calculating V17. So we are now considering what is the probability that the first tag after the start symbol is the 7th tag, is a determiner. So that's the transition probability. See, the probability of changing from one tag to the other tag. We must multiply this value by the emission probability, which means that given that we see or we believe that the tag is a determiner, what is the probability it will produce the word Janet? Now you may want to go back to the previous slides where we have the matrix A and matrix B. You can check that the value of given start symbol, the probability of transitioning to dt is 0.2026, and then the probability of a determiner producing the word Janet is 0. So now actually if you must write a value here in this box here, the value is 0. By the way, if you need to look at the table, you can open that table in a different screen or so on. I will give you the link to the Juravsky PDF in the description. You may obtain the A and B matrix from the Juravsky's PDF, and then so you can open that PDF and you can open this screen so you can really look at the values on the matrices A and B. You need to calculate all the VIs, V1, sorry. So from V17, V16, V15 up to V11. You really need to calculate each of this square here. Now let me give you an example of V14. Same as before, you start with the transition probability. Check on the table matrix A, what is the probability of transitioning from the start symbol to JJ, an adjective. You can check the value is 0.0453 from the table. And then what is the probability? Now you need to look at the emission probability. What is the probability that an adjective produce the word Janet? Again, it's a 0. So you can see here it is written that the value is 0. You need to compute V13, V12, and finally for V11, things get a bit more interesting. So V11, again, you start with the transition probability. From the start symbol to the first tag is proper noun. Then you get this value from the table or matrix A. And then multiply it by the emission probability, that the tag produces the word that we see, Janet. So now you can see the value is not 0 this time. It is 0.00009. Okay, so you already compute the value for V17 up to V11. Next, we are going to move on to the second word. The second word is the word will. Same as before, you need to compute V27 all the way up to V21. Here I give you an example of how to compute V22. Now, the first thing is you should notice that there are always two components, transition and emission. Okay, but now we see that all the possibilities that lead to this second tag can come from any previous tag, because we don't know yet what is the correct tag for the first word Janet. So we need to consider all the transitions from all the possible tags into this tag. Or in other words, we try to see what is the probability that the second tag is a model. The second tag is a model. But we need to consider the transition from all the possible tags in the first word. So we need to consider if the first word's tag is DT, if the first word's tag is RB, if the first word's tag is NN, up to if the first words is NNP, proper noun. So how is the calculation? Calculation is you multiply the value inside the square, like V17, times the transition probability from the tag 7 to tag 2, so from tag DT to tag MD, times the probability that the tag MD will emit or produce the word will. Now, because we have all possibilities here, we don't want to calculate everything. What we want is that from all possibilities, we take the max. So apparently the maximum here is this. You can verify that this is V11 that we have in the previous slide. And this is the transition probability for matrix A. And then the value is this 0.9 to the power of -8. So again, this is the multiplication of the value inside the box times the transition probability. But to get the value for V22, remember that you need to multiply it again with the emission probability of the word will. So let me summarize all the steps. So to calculate V22, you need to consider all the possible squares in the previous word. So you need to consider V17, V16 up to V11. From each square, you need to say that from that square, you need to have a transition. So square 7 corresponds to the tag DT, determiner. You need to say it is transitioning from DT to MD. Okay, why MD? Because you are calculating V22, and 2 is the tag MD. So you multiply V17 times the transition probability from from DT to MD, times the emission probability that the tag MD will produce the word will. Okay, you can do that for all rows, or as it is shown here, you find the maximum first among all its multiplication and then multiply it with the emission probability. So you keep doing that for all V2, so V27, V26 up to V21. Again, you need to consider all the previous possibilities. And do not forget to multiply it with the emission probabilities. Once you have completed all the values for all the V's, at the last V, V5 here, you pick the square with the largest value. And then from there, you trace back which box gives you the maximum to this box. So you're tracing back your steps, which previous box gives you the maximum. Now, once you have traced back all these values, you know that, okay, so the correct tags are, the first one for Janet is the first tag, proper noun. For Will is the second tag, model. For the word back is the third tag, verb on the base form. For the fourth word, the is the seventh tag. And then finally, for the word bill, is the fifth tag, noun. So that's how you obtain the best tags, the best sequence of the tags for the given sentence. And this is the pseudocode for the Viterbi algorithm. Really, the most important things are just these two steps here. So Viterbi here is the V boxes that we've seen before. For example, V22. Here it says that you need to consider all the previous boxes from the previous word. So remember, when we compute V22, you need to consider V17, V16, V15, V14, V13 up to V11. So that is what is written here, times the transition probability, A, times the emission probability. And among all those possibilities, you pick the one that is the maximum. And here, back pointer simply means that you need to record or keep in mind when you are at, let's say, V22, you need to record which V1 gives you the best value when you compute V22. So you keep that, I think V11 gives the best maximum value for when you're computing V22. So you save that thing, and it is called the back pointer. Why do you need to save which box from the previous word gives you the best value? Well, because remember, when you have solved up to V5, you need to trace back your steps to V4, V3, V2, and V1 to get the best tags. So that's the end of this presentation. I can understand if it feels a bit too much for you in this hidden Markov model, but if you really look at all the computation closely, really it's not that difficult. It's just a lot of work, yes, and you have to trace back, you have to trace this is coming from that, multiply by that, but really the work is just consider all the boxes from the previous word times the transition probabilities times the emission probabilities. You get the value for that particular box, and just keep filling all the boxes for the values, and then once you finish with the last columns of the boxes like V5, you find the maximum among all V5s, and then you trace back your steps to get the best sequence of tags. Now you might think that to do this, you need to have a corpus that is already labeled with the correct tags, such that you can have matrix A and matrix B. Yes, that is correct. But what if you don't have that kind of corpus? You have the documents, you have the tag set, but you don't have the tagged documents. Well, in that case, actually hidden Markov model can also be used to learn such thing in an unsupervised way. But that is a bit more complicated than this. So I hope by this introduction, later if you really need to apply that kind of hidden Markov model from scratch in an unsupervised way, you know that it is actually possible. Okay, so as usual, if you have any questions, feel free to leave your questions in the IDE forum Q&A. You can also send me an email or leave your questions in the comment section. Thank you.